Okay, good morning, everyone. Today is our final lecture, and technically, what I'm going to cover today, I've already actually covered most of it already before, but I got a lot of concerned emails about this section and a little bit of panic about this section of work. So I kind of want to just go through everything just one more time to, just try and cement some of the concepts for you. And also may need to also just hopefully explain why some of the stuff is important. So the explanations of why it's important is not like a really big deal for you guys because you just have to do the step-by-step process. But I do want you to actually, just have a little bit of a connection with what is happening behind the scenes and why it's like that, because it may just help you understand the step-by-step process even further. Side notes, if you have been checking the YouTube playlist, you'll see I uploaded a couple of me just using pen and paper to go through some of the work. So you will have additional content to look at if you're still epic, confused or lost in regards to that. Okay, so what we're going to do now is I'm just going to start off from the beginning to remind you about a lot of what exactly is the table doing? What is it representing? So I'm going to start from scratch in regards to this is what the table is actually telling you. And this is what those non-empty cell values are basically telling you, because that's going to help you out. Right, so let's start off with just a fresh page. And let's just write a table in here. So I'm just going to choose an example to form a table. So we know we always have a from and a to, right? And then we have obviously to, it's your suppliers or whatever your warehouses and stuff are. We give them names. You don't really care that much about the names. And then we have, the supply. And then we have obviously from, and I'm just going to do X, Y, Z here because we don't really care about that either. And then we have our demand chilling over here. And then we'd have 300, 200, 200, and then the 700 and 700. So when we're doing these things, when we're doing the table only works when the supply and demand are equal. And I'll show you how to fix it if they're not equal a little bit later. So just be very careful about that. The fact that this is 700 and this is 700 is a requirement for the table. So this should actually happen. If it doesn't happen, you have to fix your table. Right. Now, we also spoke about this again last week, and we said they give us the cost of shipping from, the warehouse to the factory to the warehouse. So these are usually your factories producing your product. And then you have, what you're shipping to sitting over here. And all your individual ones, there's a cost associated with it. And I tend to call them X11, X12, and that because it just makes sense kind of a thing. And it's whichever one sits here is 1, 2, and 3. And obviously here 1, 2, and 3. And this is your, your column numbers, and your row numbers are the ones obviously chilling down here. Because remember, it's representing in that direction. So we have X11, X12, X13, X21, X22, X23, and X31, X32, X33. And remember, when you write this, it's like Xij, where I is your factory, and J is the warehouse. And then you're basically saying the number of units transported from the ith factory to the jth warehouse. So when we're looking at this table, when we're talking about the empty and non-empty cells, we're talking about the decision variables, which are represented by this, over here. But we also have the costs associated with transporting 1 unit from the ith factory to the jth warehouse. And we had that, we put it in the top, right corner. So we have like that 5, the 4 and the 3, the 8, the 4 and the 3. And again, this is coming from an example. I'm just using it to explain how you can read this table. 9, 7, and 5. And those are the costs associated with transporting one unit from the I factory to the J warehouse. So that's your entire table. But what this is actually also telling us is that we have our constraints, right? So we have our demand constraints, which are the column constraints here with the demand, and over here, and over here. Now, when you have a demand, you have to meet it, right? So when we have this, what this is actually saying, it's saying, for our column constraints, x11 plus x21 plus x31, and it is a demand, so it's a case of you need at least that much. And I think this is where I may have messed up and kept on going back and forth with the explanation last week, so I want to just reiterate it. You have that must be, greater than or equal to 300. It must have it when they, because factory A requires at least 300, the shipping the units from the warehouses, 1, 2, and 3 have to meet at least 300. But I'll explain again why the greater than sign is not going to be an issue later on. And I'm going to explain it based on another example as well. So 1, 1, 2, 1, we have this as well. So the next column, 3, 2. And then we have 1, 3 plus x23 plus x33 greater than or equal to 200. And those are all the demand constraints. And you can also write this as, you have your summation. You'll notice the thing that changes is, okay, and okay, cool. I am doing it the correct way around. So notice the thing that changes here is your I. Your J stays the same. So you're running through your I's, 1 to however many you have. So however many, rows you have, because those are the things that are, changing. And then you'll be like, okay, so that's the 3. And that is, the sum of, and then you'll have your I and you'll have your J. And then you're going to have something connected to your J value, because you'll notice the J stays the same. And there's a very specific one to it. You don't have to stress about this. As long as you understand this part here, you're good. But that's not the only constraints we have, because we have the constraints on how much the warehouses can actually produce. So we have, the constraints sitting here like this, and like that, and like that. So let's write down those constraints as well. So we have x11 plus x12 plus x13, and they can only make 100. That's the maximum they can produce. So we have, that less than or equal to 100 situation. Then we have the next, row, which is 21 plus x22 plus x23 less than or equal to 300. We have the next row there, 31 plus x32 plus x33 greater than or equal to 300. And those are your supply constraints. Okay, so supply. But we're not done, because this graph, or this table, sorry, not graph, also gives us the actual objective function equation. So I know it looks scary at the moment, so I'm going to just try and, neaten it up a bit. So we've handled the constraints, so we know where they sit on both of them. Okay. We know that those are warehouses, factories, and everything. Now, if we look here, the objective function is related to the cost of transporting everything. So we have, the units for everything there, and the cost of transporting one of the units sitting over there. And it continues for the entire thing, for this entire piece here. So we actually have that objective function equation sitting there in the middle of our table. So we actually have is 5x11, that does not look like an x, plus 4x12 plus 3x13 plus 8x21 plus 4x22 plus 3x23 plus 9x31 plus 7x32 plus 5x33. So when we tell you what is the optimal solutions cost, that is where you'll get it from. So you'll use whatever values are actually in those folders for the x11, x12, and everything to utilize that. So that's the objective function equation. Okay. So that's where what the table looks like and how it actually relates into equations. Now what we're going to do is we're going to discuss the northwest corner method, and actually it's going to help us understand, why things work the way that they do. So if we go to the northwest corner method, so we have this, currently we don't actually have anything in these values, but we do know that whatever we put in the middle there of the x11, x12 are going to be our decision variables. So I'm talking about this here. So currently it's blank, right? So the northwest corner method is going to give us our first extreme point. Now, if you think about your extreme points, and let's just go back to a two-dimensional problem, we know that when we have an optimal solution, it's going to occur at a corner point. So what I'm going to do here, I'm doing this on purpose. Okay, and let's say everything above this line is, our feasible for one of our constraints. Let's say everything on this side of the line. Yes, do you have a question? Okay, let's say everything on this side of the line is feasible. So this is just a random example because I want to discuss the corner points. And then say everything below this line, but also everything below that line. So our feasible region in this example would be, and this is just a random example, it's not connected to that table, would be this piece here, right? Because that's where all the constraints are being met. So that's the feasible region. And in this situation, we know that the optimal solution is going to be at one of these corner points. So we know this from the corner point theorem. Now, the corner point theorem can be extended from, just a two-dimensional system to a system where, you have a lot more dimensions happening. And the idea is what we call a corner point is actually an extreme point. And we know that our optimal solution will still occur at an extreme point. So you can think of it like a corner, but technically it has a name. It's an extreme point kind of name. But now this is going to be a slightly important situation here to consider with our transport equation and everything. Reasons why that n plus m minus 1 is actually, applicable in regards to this. You'll notice in this graph that I just did, there was a constraint over here, which it's being met, but it's not, being met on the line. So this isn't playing a role and that isn't playing a role. So when you look at the corner points and you look at, your values, you will see that the yellow constraint doesn't really make an impact. It's not binding, and by binding means it's not contained, it's not on the boundary of that feasible region. So while it exists and it's great and everything, it's technically represented by this one here. Now, it's not going to always be this neat where it's parallel, but the idea is there will be some constraints which can be made up of the other constraints. So it will not play a direct role in your corner point in regards to that. So that's where this, the m plus n minus 1 is coming from. The way that we set up our transport equation with the fact that it's linear and we have, the rows and the columns for the supply and demand, and the fact that they equal is going to have a situation where one of those constraints are always going to be able to be written as the other constraints. So when you go back to this, one of these, and you can go ahead and play around with it, you can use simultaneous equations to create one of these constraints from the others that are left behind. And it's always going to be that situation that you can do it for at least one of them in regards to it. So that's where that n plus n minus 1 comes from, is that one of these is going to be represented by the others. And then there's some background math that we're actually doing. And the background math is connected to this linear independence that we talk about. Linear dependent if it can be written as a representation of the others, which means these ones here are at least, linear independent. And you don't have to know about this, but the idea is we're actually utilizing matrices, and we only take the ones that are linear independent for our x values. So you'll notice our decision variables are connected to these linear independent constraints, and it's because we need a square matrices so we can invert it. Now, this is not a big deal that you need to know about, but the idea is your decision variables are connected to those linear independent constraints, and that's why you need the n plus n minus one of them or that are non-empty, so that you can do the behind the scene math, which is what those R's and the K's that you're doing are actually producing. So again, you don't really have to know about it in this course, but I figured a little bit of context will make it a little bit, less dislike towards it. You're like, okay, it actually has a purpose. There's behind the scene math that requires you to have so many decision variables because of the linear independent variables. And that's going to, make it a little bit easier to go like, okay, fine, I'm okay with doing this rule. And it's connected to like this kind of situation. Now, one of the other things that if you look at this diagram and you look at these corner points, when you look at this corner point and you use that corner point, what you're actually saying is at that moment in time, this constraint here, even though it's a linear inequality constraint, so it has that situation where everything on this side of the line works. What's actually happening is when you're making up that point, the equality is the thing making up that point. It's the line itself. And that's going to play a big role, particularly because we are utilizing, our extreme points for like our northwest, and then even later for our different iterations, which is why that greater than and equal and less than situation is not a big deal in regards to it when we look at the equality. Because at that moment in time, we want an extreme point, and at the extreme point, certain constraints that make up that corner point or that extreme point are going to be the equal. They're on the line itself. They're not including all of this piece here because we're looking at, where the equalities are being met. So that's just another thing to just consider, particularly when you do the northwest corner method and when we do the different iterations. Okay, so now let's go to the northwest corner method. So I'm going to draw that graph again. And yes, I'm drawing everything from scratch because I'm trying to just bring in the different contexts to you. So let's just write that table again. So from and to A, B, C, supply X, Y, Z, demand. We have that. Pretty badly drawn table, but I think you get the point. We have the 100, we have the 300, 300, 700, and 700. 300, 200, and 200. 5, 4, 3, 8, 4, 3, 9, 7, 5. And I just want to do something quickly because I don't want to keep drawing this. Okay. And from current slide. Okay, so now with the northwest corner method, it starts you off and it's just going to put you in one of those corner points. So if you had an example like this, when you work it out and the way that you work it out, it will shove you in one of these with the method that we're using the method of the fact that, we have those equalities coming through. So if you start off with the northwest corner, it starts off with this one. And then we look at, the demand and the supply, and we choose the smallest one. Because remember, when we do that, when we're looking at this point here, we're actually saying X11, and let's change the color here so we know, because we have that's X11, that's X21, that's X31. So saying X11 plus X21 plus X31 equals 300 because we're trying to get it so that, that constraint is literally, at the most extreme points of it. So it's the boundary of it. So that constraint is inequality instead of an inequality. But it's also saying, the fact that when we look at it, we have the x11 and then plus the 12 and x13 equals to 100. So we have to choose the smaller ones so that we can get both of these constraints, being true. So we choose the smallest one of it and we put it in. And when we do that, we actually, replacing this with 100, replacing that with 100, we are essentially now saying that what's left over, has only, like for this example here, 200 to go. And that's why we end up, subtracting by 100 on this side like that, and then saying that's 200, and subtracting here and saying that is 0. So it's to make sure that we are aware we have utilized 100 of it. So we don't have to go back and investigate each time we put it, on that side, because, it just makes it a little bit easier for us to, do the math. And that's also why whichever one is 0, we cross out that constraint because we can't add anything to it without breaking that constraint. So when you look here at this bottom one, these can't have values because the moment they have values, we no longer have this actually happening. That 100 is equal to 100. That's why we say, okay, well, we can't use this anymore. So those can't be utilized, and then we move on. So in this one here, we still have that option of, the x21 can have a value or the x31 can have a value. So that's why we then process, and we follow the process of, again, the northwest corner. And that's just so that when we go through it, there is a procedure around it so we don't really mess up and have to jump around and stuff. So the structure helps us get the easiest of those optimal points. There are many other ways that we can find initial basic solution. This is just one of the quickest ones. So now we're sitting at the x21 and the same thing happens. So you have those, constraint equations. So we know that this one has been met, so that goes away. We're still working with this one here, right? But now we're working by figuring out what this one can be, which means we also need its row constraint. So that x22 and that x23. So we have, x21 plus x22 plus x23 equals to 300. Then when we look at that process, we know, okay, what do we have to play around with? In this case, we have that 2
Yo, kwenzakala ini nala?
Miss Tricia, your mic is muted.
Can you guys hear me? Apparently my recording dropped at some point.
Yes, ma'am, I can hear you.
Okay, thank you. Right. So we have, that situation where we check our basic variables to go through all the process of just making sure they're links up for the math to work, which is the behind the scenes stuff that you guys don't overly have to stress about, but it is connected to the number of linear independent constraints. So here we have the 5, we don't have to do anything to it. Remember, if we didn't have the 5, we could just add in, the zeros. Did I stop sharing the screen? Oh my gosh, I'm sorry about that. Okay, there we go. So we have, those 5 that are actually working out to allow us to do the behind the scene math, which is actually taking the inverse to solve for our decision variable. So again, you don't have to stress about that, but that's actually what we're doing behind the scenes with the rows and the column numbers. We're actually inverting a matrix to solve for the decision variables. Right. So that's why in Modi's method, we actually get the R's and the K values, and we use the cost coefficients and everything to go about doing that work. Right, so let's go ahead with the Modi steps. So the Modi steps, there's a few of them, and I'm just going to simplify the process a little bit by giving you the bare basic steps. So Modi requires firstly an initial basic feasible solution. In your case, that's the Northwest method. Again, there are tons of methods out there available. Once you have the initial basic feasible solution, you jump into what is Modi's method. And the first thing you do is you find your R's and your K's, which is connected to your basic variables, and the basic variables are just those non-empty cells. Okay, so you use the non-empty cells. And again, this is connected to inverting a matrices. So if you've done any of that stuff, it's basically doing like a reducer echelon kind of stuff in regards to it. I understand most of you have not done that, which is why you guys don't get all the behind the scene math for this method. But it's connected to the non-empty cells. And we just use the formula where we have the Cij is equal to the Ri plus the Kj. So you have your cost coefficient. It's equal to your row value and then your column value. That's what you'll use to work out everything. But what you'll do is when you're finding your R's and your K's and the non-empty cells, you will always set your R1 to equal to 0. This is not something that's done in all Modi methods. So if you start using the work online, be very, very careful about that because I know there are calculators online. They don't necessarily always make R1 equal to 0. There is other methods that you employ with choosing which of your R's or K's would be 0. So be very careful about that. In this course, R1 is always equal to 0. Once you find your R's and your K's, we then move on to the next step. And the next step is taking those R's and K's. So taking R's and K's, and what it's going to do, it's going to work out the differences, as in it's going to work out how much effect would be bringing in one of the non-basic variables, those empty cells. So you'll notice I use the word basic and non-basic variables, again, because I know the math behind it, but it's the empty cells. And the empty cells are where your decision variables are just chilling at 0. They're not playing an active role. So it'll be a case of what would happen if you made those ones play a more active role. And so the constraints connected to them, become those binding constraints, those equality constraints. So you take those R's and your K's and work out the difference. And the difference is going to be like, what is the difference if you add 1 unit of those non-empty cells? So basically moving them from, like xij equal to 0 to xij equal to 1. What's its impact going to be on your objective function? So we have an equation for that. This is the only part you really need to stress about, which is your cost minus your row value minus your column value, which you can just write as this. Or you can flip it around and write it as, the column number first and then your row number. So you'll notice these R's and K's are super important because they're used in your differences to determine, the impact of them. Then you're going to have a situation where you investigate the differences. So this is the part where it actually, you can figure out if it's at optimal or not. And that's where you check your difference values, all of them, and you investigate. So if they are negative, it means they're going to reduce your objective function. And that's obviously if you're doing a minimization equation, that's important. If they, if all of them are positive and only one is like equal to 0, that just means that you have another solution with the exact same optimal value. So let's not stress about that one at the moment. Let's just stress about, is it optimal or not? So if there's one that's negative, even a single one, you can still reduce your objective function further, which means you have to do another iteration. If they're positive, you're at optimal. Again, you have that 0, 1, but let's not stress about that. Let's focus on, negative and positive kind of situation. So step 3 is the actual check for optimality. Obviously, if it's not optimal, in other words, one of them is negative, you continue your steps. So the next step is you select the largest negative. And that's just thinking about the fact that if this is representing the difference to your objective function, so how much your objective function value is going to alter, you want the one with the biggest impact. So you select the largest Dij, and that block is going to become non-empty. So it's going to become a basic variable, a variable that plays an active role in your optimal solution. So in other words, it's going to move usually from 0, but technically you can have 0 as a basic variable. Take that block as a non-empty block. Okay, so that would be your next step in regards to everything. And this is the part that gets slightly frustrating, I think, for most students, because once you have this, you have to consider, okay, if that one's coming in, one of your other decision variables needs to leave. So it's a case of one of them has to go away. How do you select that without impacting all your constraints? Because remember, your constraints still have to have those equalities being met because that's an extreme point. So how do you go about, making sure that that's still going? That's when the loop comes in, but I'll explain it when we do an example there. But the loop is to ensure that the constraints remain met. Okay. And then once we have the loop, we have the parts of the loop where we look at the negatives. And when we look at the negatives, again, that's so the constraints are being met. So when you talk about the smallest negative, it's to have the constraints being met, and that's the value that comes in. And then we start the process all over again until you stop, until that third step breaks the situation. So let's go through just, one iteration of that, so just to remind you of what's going on, where is it going on, and all that kind of stuff. So we go back to that over there. We've checked that we have 5 of them. If we didn't have 5 of them, again, we could just put in a 0. And now let's do some working out. Okay, if my pen works. Right. So the first thing we're going to have to do is find those R's and those K values. So we have, that Cij is equal to Ri plus Kj. And we can do this without excessive amounts of thinking, because we have the case of whenever we use the cost is connected to that R value and then that column. This cost will be connected to that R value, obviously, and that column value. So as long as you remember that pattern, you kind of, good on that front. But if you do get, lost, you can always go and link up and say, I'm looking at C11, which means I need R1 plus K1. Or I'm looking at C21, which means I need R2 plus K1. Or C23, R2 plus K3. So if you do get lost, you can always, look at it like that. Right, so let's go ahead and play with those R and those K values. You choose the one where there's only one unknown. So that's why we actually have a nice little starting point with R1 equals 0. Because now we say, oh, well, we have C11, which is that 5, minus row 1 is going to give us K. And that's just making K the subject of the formula. So remember, we can make K the subject of the formula by just taking that R across. And that's where that negative comes in. So let's go ahead and say 5 minus 0, and that gives us K1 is equal to 5. Then we'll go to the next non-empty cell. And you would go through the process of making sure you choose the next non-empty cell so that you only have one unknown. So it's not always going to be super neat. You may have to search for the one which has one unknown, but the idea is just look for that one. In this case, it is going to be this block over here, because you have that K value, you have that cost value, you don't have that row number. So, you have a solution that you can find. Obviously, if you're looking at the others, you would end up with 2 unknowns, and you eventually, be able to figure out which one you should be looking at. So again, in this case, we need to find R. We can just make R the subject of the formula. So it's not, hectically stressful here. We just take the K across. And you'll notice it's again cost minus the column number. So when you look at this, you can say 8 minus 5 and gives you the row, which is 3. So you see there's a nice little pattern forming there. And we do it for all the non-empty cells. So we go through the process. So this one, we have R, we have cost, which means we can work out what the column is. So we have the 4 minus the 3 gives us that 1, and that is K2. And then we, follow the process again. We have the column number here, we have the cost here, which means we can find its, corresponding row number of 7 minus 1, which gives us the 6. And then we have the row number and the cost, which means we can get the column number here. And that's going to be 6 minus 5, which gives us the 1. Just want to make sure my math is correct. Okay. So that's how you get your rows and your column numbers. Now remember, your second step is to actually find your differences. So just a reminder about that. Your second step is to find the differences, and the differences are all those empty cells. So now you're going to find values for the differences, and you're going to put them in this left, corner. And you utilize the formula of your difference is your cost minus your row number minus your column number. Okay? So you just go to any of the non-empty cells. I'm going to start with this one. So you have 9 minus 6. That gives us 3 minus 5. And that is going to give us minus 2. Okay, so I just had to check my math there. It's 9 minus 6 minus, oh, my math is wrong. No, minus 5, that's fine. 9 minus 11, that is going to give us 2, negative 2. We can do it for all of the others, and I'm going to specifically do it in a not great order, so you can see it's still going to work out regardless. I'm going to do this block over here now, and that is 3 minus 3 minus 1. It's going to give us minus 1. Then we go here, we're going to have, 3 minus 0 minus 1, minus 0 minus 1, and that is going to give us 2. And then we have 4 minus 0 minus 1, and that is going to give us 3. So now we interpret this. We're like, well, we can actually bring in increase, essentially when what we're saying, the x31 or the x23, and it will reduce our objective function value. So remember, we have an objective function value at the moment, which is that 5 times 100 plus 8 times 200 plus 4 times 100 plus 7 times 100 plus 5 times 200. But we're saying if we bring in, so we increase the value of x23 or x31 by a single unit, they are going to decrease that objective function value. Obviously, the more units you bring in, the more it's going to reduce that objective function value. So that's why we're looking at those d values. We choose the largest negative because it's going to have more of an impact, because obviously we don't want to do this forever. We want the answer as fast as possible. So we want to go along the most extreme path. So we're like, okay, well, that's the largest negative. So we're going to bring in this one over here. So that's what we're saying. We're going to move x31 from equal to 0. We're going to increase its value. So we're going to not bring it into this table. But when we do that, remember, and we spoke about this with the northwest corner method, we still have to maintain our constraints. And this is where that loop comes into play. So remember, when we have this and you're like, well, x31 is going to increase. We look at the fact that, and let's just look at this column here, for example. We have that x11 and x21. So we have x11 plus x21 plus x31. And it is equal to 300. So when that's 100 and 200, remember, it's at the extreme point where the equality is being met. We have that situation. So we have that's currently 100. That's currently 200. So obviously, if we want to increase this value, we have to decrease one of these for, that still to happen. And we also have it for this row. So we have that other constraint happening. Remember, that's x31 plus x32 plus x33 equal to 300, because again, it's at the boundary. It's where it's a binding constraint, where it's an equality constraint. That's currently 100. That's currently 200. So if we want to increase this one, we have to decrease one of those. So this is where that loop is coming into play. We want to keep those constraints. That's why we have to investigate which one of those can we actually decrease and still keep our constraint. Because right now we have a case of, okay, let me just choose the yellow at the moment. Either that one can be decreased or that one can be decreased. And then we have that one can be decreased and that one can be decreased. But we're left with the situation of the moment we decrease, moment we decrease x32. So let's use x32 as an example. It's going to mess up wherever x32 features, which means when we look at that, there is one additional constraint. So x32 features in that constraint, but it also features, down there like that. So we'll have a situation of, x12 plus x22 plus x32 is equal to 200. So if we had to go and say, okay, fine, we decrease this, and it's currently 100, and that's currently 100, right? And this is currently 0, and it's not featuring. If we decrease that one, we have to, still keep everything, the constraint being met as an equality kind of situation, which means we have to increase this one here. And we only look at the ones where there are non-empty values, so the ones that are positive values for this to play out, because we're trying to keep it at that extreme point. So we're trying to keep it at the extreme point. We're not trying to have it in the boundary, in the inequality side. So we have this, just to play with. We don't have this one to play with. We only have this one because that one has a value to play around with, even though we just increase in it basically. So we have a situation of, well, to keep this as, equal to 200, we have to increase this x22. Right. If we do that, guess what? That x22 plays a role in another constraint. And that's where that loop comes in. So you want to keep it, obviously, as little constraints as possible being messed with, but you are going to need a minimum of 3 other constraints to, have it so that everything works out. Because now we have that x22 constraint is affected, which means where else is x22 utilized? And x22 is also utilized in x21 plus x22 plus x23 equal to 300. Then we're like, okay, we increase this one, which means we have to decrease one of those. And that's where that loop is coming from. So just be very careful about it. It's that impact, from one to the other kind of situation. And that's why we have that loop. So when we look at this and when we investigate it, we do want to create like when we talk about a loop, it's basically a square or a rectangle kind of effect. And it's just as little as possible. You want as little as possible, changes, because this gets hectic. You've seen it here with just these, 3 equations, 4 equations technically. It can get quite hectic and you want to minimize that impact. So we have that situation of when you're looking at these and when you're investigating them, you do want this kind of like a jump, and you want, obviously that kind of a jump situation. So there we have the loop now. And obviously if that's negative, that must be positive. So when we write the loop there, we actually just doing what we did here on the table. So we're saying, hey, there's that positive and that increase and that decrease. So we're just doing what we did with the equations on the side on the table, because it makes it obviously a lot less work for us to do. So we have that loop, and now we have to consider how much can we mess with it. So how much can we, change that x31? So remember, the original one was, this equation here, and it was, that equation. Hold on, one. Where did I write that equation? Okay, so we have the x11 equal to 300, and then we had it's this one here. So those are the 2 original equations, right? So when we look at that and when we're investigating, we know we can decrease, either, or we're actually utilizing, the 2,1 and we're utilizing the 3,2. How much can we decrease that by? So 2,1 is 200 and 3,2 is 100. So technically we only have 100 to play around with to keep that constraint. So when we talk about the negatives, we look at the smallest negative or the smallest value where we're going to decrease from and utilize that for our increase. It's to maintain these constraints. So those 2 main constraints that we had. We know that we're going to bring in this one over here. We're going to decrease from it, or we can decrease from this one. And obviously to meet our constraints, we choose the smallest one because we can't remove 200 from here and keep our constraint. So just be very careful about that. That's why we use the smallest one. Now we're like, okay, we're going to take 100 because 100 is the smallest. I know my graph is looking very, very scary right now. So we make x31 100, and then obviously we have to remove it from our x21 and our x32 and add it to our x22 sitting over there. So when we remove it, and that's just to keep all our constraints being met. So let's just use a new piece of paper there to make our lives a little bit easier. So we had that 100, we had that 100 over there, we had that 200, and then we had, we want this one to come in, the 3-1. And we're like, we want that one to come in, that's positive. So in other words, that one must be negative, that one must increase, and that one must decrease. And that's from that, making sure all our constraints remain met. We know that we choose the smallest one to make of the negatives for our constraints to be met. So now this becomes 100, this becomes 0, which means it becomes the empty cell. This becomes 100, and this becomes 200. Everything else remains the same in our table. So we have that 100, we have that 200 still chilling there. So we have a new table that shows up. So let's just remove all the green in that. So our new table is essentially just that. And then guess what? We start the process all over again to check everything. And we keep on doing it until all our differences are positive. So there's a process. If you follow the process, it'll work out just fine. And I think once you start seeing that your selections are based on keeping those constraints basically equalities, it's a lot easier for you to get what happens there. Some of them will become inequalities again. That's fine, because you're still going to have your n plus n minus one of them being equalities. So when you do it, there will be the binding ones. There will always be n plus n minus one of those constraints are going to be binding in regards to that kind of situation. And binding means they're equalities. Okay. Now, I want to do one more thing here right. I keep on talking about the fact that our supply and demand have to be equal. How can we fix our table if it is not equal? So this technically isn't usually examined, but I do want to just show it to you because it's a very useful thing. It's also a case of it's actually not that of a big deal to change your table in regards to this. So let's go ahead and just do that. You have a question? Okay. I'm just going to write a random table to go through it. So this example may not necessarily work out in real life, but just like the idea is just to show you how you can fix it. Okay, so I'm going to have A, B, and C. I'm going to have 200, 300. Then I'm going to have X and Y. And then I'm going to have 50, 50, and 100. So you have 200 there and 500 over there. So remember, when you're working out your supply and your demand, this adds up to this piece here. And this adds up to this piece here. And the only time you can use Modi's method and northwest corner method is when this one is equal to this one. So how do we fix that? We fix that by actually just adding in a dummy constraint. And a dummy constraint is going to be applicable as either going to be a demand constraint or a supply constraint, depending on which one needs to be increased to get it to be the other one for them to be equal. So you'll increase one of them so that they become equal. In this case, we want to increase the demand. So what constraints impact the demand? The column constraints, right? Because the demand constraints are sitting in this order over here. That's a demand, that's a demand, that's a demand. If we want to get the 200 to 500, we need another column totaling 300, right? And that's actually what we do. We say, okay, fine, we need another column totaling 300. So we shove it in there. and we rewrite it. So we say, okay, just move this across. It'd help if it didn't rub everything out, but you get the point. We bring in another column. We label it 300 as a demand, and I'll show you now why it won't make a huge difference. Okay, we still have the supply, and I just want to remember that was 200, that was 300. Now, when we add up our demand, we get that 500. So we have, that's working out. But now you're like, okay, but there is a new constraint there, and we don't want this constraint to count. So there's a couple of ways that we can, you work it out like that. So we don't want this constraint to count in the objective function. So what's impacting our objective function is the cost connected to these blocks here. So there will be costs involved over here. So let's just put in some random values, 5, 4, 3, 2, 4, 1. So we have costs connected to, transporting from X to A and from Y to A and so on. To make it not count an objective function, remember your objective function is taking this 5, multiplying by this x11, taking this 4, multiplying by this x12, taking this think 3 and multiplying by the x13 and adding them all together, this process. So what we do is, let's just finish writing this. 2, 3, got the 2. What we do here is just say, okay, fine, that's 0, because then it's not going to impact our objective function. So it's not going to impact our objective optimal solution. So we make these costs 0, and then whatever values we put here of the x14 and the x24 is not going to impact our solution that we're searching. So it fixes our table. It gives us the constraint that will make it so that, everything works. And we will get values for this, x14 and this x24, but it's not going to impact our optimal solution. It's not going to impact our objective function because those zeros are chilling there. So that's how we fix it. It's actually, a really quick fix. That fix where you say, well, 0 times something, it's not going to have an impact. There is the situation, and you do the very similar situation if it was the other way around, and as in your supply, was smaller than your demand. So let's just go through that quickly. X, Y, I'm making this even smaller now because the idea is just to allow you to see what's happening here. I'm going to leave space as well because I want to be sneaky about it. Demand, let's say that's 5. That's 5. That gives us 10. Let's say that's 2, and that is 7, and that gives us 9, right? So your supply and your demand are not equal to each other. You will add in a constraint increasing your supply. So you would add in this case, you would want a 1 over there to get it to 10, right? So then you just add in another row, and you have zeros for that row. And then you have, it's called a dummy row kind of situation. So you'll have, your x31 and your x32. They'll be added to your objective function, but they won't impact your objective function solution and your optimal solution. And that allows you to do all the math again with the fact of we want to invert the matrices. We need square matrices particularly to do with everything. And in order to have that m plus n minus 1 working out, we need our supply and demand to be equal. So the background math just requires that. And this is a quick fix to trick the math to allow you to do it. So if the supply and demand aren't equal, you just create a fake constraint to, handle the difference between them, and you have their cost coefficients for that fake constraint equal to 0. How do you handle if the n plus n minus 1 is not, working out with the decision variables? You just add in you take from one of your empty variables, you shove in the 0 and you make it non-empty, and now it's kind of like active, and that's how you fix it. So those are the 2 ways that you will fix it in this module, in this course, and that is it. Now, I've obviously been speaking for quite a long time. Are there any questions relating to this? hopefully what I said was a little bit clearer this time around. You can see where it's coming from. R3 equal to 6. Okay, let me just go back there. Hopefully my math isn't wrong. Okay, so again, it's the non-empty cell. I don't know if I can use color I have not used. Okay, so the non-empty cells available was this one and this one. But we had the K2 equal to 1. So we have 7, that's 7 over there, minus the 1, and that gave us that 6. So we use this formula over here. It's called Trish, but it is linked on your actual channel where I do these, where I host these lectures. But what I'll do is I'll add the link again into this chat just so that you have access to it again. So what I did is I did another example from scratch, the entire thing, and then I also went through this stuff an additional time just to like cement this section of work, because I know it looks scary, but I promise you it's actually not as scary as that looked at the moment. It's just a case of you have to get used to the routine of finding the R's and finding the K's and then finding the D's. And then once you do that, you know, it becomes almost like routine for you to do it. So looks scary at the moment because there's a lot of extra information, but I promise once you just follow the steps, it becomes a lot quicker and a lot easier for you to do. But it does require a little bit of practice. The upside is obviously the examinable content is usually like do one iteration kind of a situation because no one has enough time to do the entire thing. Let me go and link channel again while I wait for any additional questions. Okay. So just a heads up, if you look here, you'll see the 2021 and you see the 2022 playlist. Teams takes very long to do it, so I'm going to do it from this way. Got how to do this. Okay, there you go. All right. So the link is now in the chat as well. Any additional questions? Like I said, we're actually at the end of the content, so obviously we're kind of done. So any questions, please let me know. There is no lecture tomorrow. I will answer the email still, obviously, but it's now just practice content-wise. And I'll also, hold on, I wonder if I have it still. I rewrote the Modi steps, so let me just forward you the Modi steps one more time. If you had this one and then you go through it, it's a lot of words, so just highlight the things that are important, like find the R's and K's, find the D's, do the construct loop when you're doing your process. Desktop, save. Okay. Don't know why I didn't want to do it. Again, I'm just adding some extra stuff for you guys. I rewrote the Modi steps to be a little bit more clear about using the Northwest method first. Okay. So any questions, please let me know. Otherwise, good luck. Continue studying. The test, I think, is next week. And obviously it's on the leftover content of the module. Okay, I'm going to assume there are no more questions, so I'm going to end it for us. Enjoy. Bye.